So now I will go through the different types of graphs that you need to plot for this practical. First one being a Michaelis-Menten plot. This is a plot that if you look up enzyme kinetics in your biochem textbook, this is what you are going to see. So as we discussed earlier, you have on the bottom axis the assay concentration. I'm sorry there's a bit of reflection off the whiteboard, but there's not much I can do about that. Hopefully you can see enough for it to make sense. So the assay concentration which we calculated is the assay concentration of ethanol in your tubes at the time of the assay. On the y-axis we have the velocity of the reaction. So that is what you calculated using your delta absorbance per minute times the dilution factor divided by the extinction coefficient for an ADH. So you have 6 numbers for each of your, one number for each of your 6 ethanol concentrations. You then plot velocity versus assay concentration, and that should give you a line which plateaus off somewhere around the top 2 ethanol concentrations. You can plot inhibited and uninhibited reaction on one line, on one graph, sorry. So the Michaelis-Menten plot allows you to estimate Vmax and Km. So Vmax, I've got marked here with this line where the top of your graph starts to plateau off, come across to the y-axis, and in the case of the scale that I've drawn this on, that comes to 1 micromole per minute per mil. That's our Vmax number. Come halfway down, so half Vmax, which is 0.5, come across to where your line of the reaction is placed, come down to the x-axis, and that gives you your Km. So that is the concentration at which half the active sites are filled. We can do the same for the uninhibited line, and you'll notice here that the Vmax line I've drawn is just slightly above the actual line. Now, the reason for that is, in biochemically speaking, we can never actually achieve Vmax because there are always going to be losses in the system. So the Vmax is actually just some amount above the line that we actually recorded. But I'm not expecting you to guess that. You can use the Vmax at the top of your graph here, so where your plateau appears to be. So that's the Michaelis-Menten plot. And as I said at the start, this is an estimate of Vmax and Km. We actually want to be able to achieve an exact measure for Vmax and Km. So what we do is we turn a curved line into a straight line. And we do that by taking a double reciprocal. So we take the inverse of both axes. So we have on the bottom line here 1 over S, 1 over the substrate concentration, and 1 over V to give us our 2 axes. So as you can see, this graph requires there to be negative values on the substrate concentration line. And the reason for that is that what we want to do is we want to extend our linear regression that we fit through our points which are now a straight line, and we want to extend them all the way to the axes. So where our linear regression crosses the x-axis gives us 1 over Km, and where it crosses the y-axis gives us 1 over Vmax. So to then calculate your Vmax and Km, you just simply do this calculation, 1 divided by whatever that number happens to be, and that gives you your Vmax, and the same for your Km. So in the case of a competitive inhibitor, we would expect that both of our assays, inhibited and uninhibited, would cross this axis at the same point, so that our Vmax is the same. However, our Km values will be very different. The inhibitor that we were looking at, hydroxylamine, is a competitive inhibitor, so therefore we would expect that the Vmax would be achieved even in the presence of that inhibitor. But the slope of this line will be different. So I hope that makes things clear for you. Please let me know if you have any problems. Send me an email and I'll get back to you as soon as I can.